The age of the Earth and solar system was determined using a method called radiometric dating, and today we will explore how radiometric dating works. Billions of years ago, our solar system was a primordial cosmic soup of gas and dust called a molecular cloud. The nebular hypothesis theorized that a nearby supernova triggered the collapsing of this cloud. Over 99% of the gas and dust began to coalesce to form our sun. The remaining orbiting debris eventually formed the rest of the solar system. Side note, one of the objects formed at the beginning of the galaxy formation are meteorites called chondrites. Chondrites are formed by various types of dust, chondrules, and calcium-aluminum inclusions. Because the Earth was formed at relatively the same time as the solar system, plus or minus 200 million years, scientists were able to use radiometric dating techniques on chondrites to estimate the age of the Earth. In order to understand radiometric dating, we must first understand radiometric decay. Let's start from the top. All ordinary matter is made from elements, and more. Elements are made from atoms. An atom has two parts, a nucleus and an electron cloud. The nucleus is composed of protons and neutrons. The nucleus of an atom is held together by strong interactions or strong force. It is the strongest of the four fundamental forces. Strong interaction is the phenomenon of quarks being held together by gluons to create protons and neutrons. It is also the phenomenon of protons and neutrons being held together by the same means to create the nucleus of an atom. However, protons being of like charges like to repel each other. The more protons there are in a nucleus, the stronger the repulsion force becomes and the less likely the nucleus will stay intact. Radioactive decay is the process of the nucleus losing particles. Radiometric dating is the act of measuring how much time has elapsed since a radioactive element began to decay. The rate of radioactive decay is not constant, but rather it is exponential and can be shown mathematically using this half-life equation. This equation basically says that the amount of time it takes for 100% of the parent isotope to decay to 50% is the same as the amount of time it takes for 50% of the remaining parent isotope to decay to 25%. At first glance, radiometric dating looks pretty straightforward, right? Given enough information, all we have to do is solve for t. Via some calculus magic, plug in the needed information, and voila! Problem solved. Now we can go back to watching too much Netflix. Well, not quite. This method assumes that 1. The beginning conditions of the sample are known. 2. The initial ratio of daughter to parent isotope is known. 3. The rate of decay is uniformly exponential. And 4. That there has been no gain or loss of either parent or daughter isotope in the past billions of years. Basically, this method can only be applied to a 100% contamination-free and perfect in every way sample, which is rare to say the least. To enhance the dating accuracy as well as minimize the dependency on a pure uncontaminated sample, we can use isochron dating. This method compares the ratio of the parent to daughter isotope against the ratio of a non-radiogenic isotope of the daughter element to the daughter isotope. Why? According to theory, at the formation of a meteorite, daughter isotopes are uniformly distributed, and therefore the ratio of daughter element, or d sub e, to daughter isotope, or d sub I, is constant everywhere throughout the sample. But the parent isotope, or p sub I, is unevenly distributed, so the ratio of p sub I to d sub I varies from place to place, which results in a straight line when plotting the ratio of p sub I to d sub I against d sub e to d sub I on a graph. As the parent decays to daughter, note one parent isotope decays into one daughter isotope, the ratios change and the straight line remains but becomes angled. The slope of the line equals the number of half-lives the parent isotope has passed since solidification. What if the sample was contaminated after formation? Contaminated samples will fall out of the trend line. Using lid-to-lid isochron dating on a meteorite named NWA 2364, the oldest known solid in our solar system, we found that the solar system and our Earth are approximately 4.568 billion years old.